Okay, so we're going to do today, we go on Canvas under Files and in-class data. We're going to use two different files. One is titled Expenses, and the other is this Powerlifting Small. Okay, so I think we'll start out with the Powerlifting Small. What this is a data set that has a bunch of different powerlifting meets from like all over the world, and mostly Europe and the United States. It's, in these powerlifting meets, they perform 3 lifts: the squat, bench, deadlift. So it has kind of their best lift out of 3 attempts, and then the total of their best 3 lifts, right? So we're thinking about, we've got some information on these different lifters. So we got body weight, we got age, whether or not they're male, raw, reps. So what we could do is start to look at things like how kind of try to predict this total weight lifted. It's in kilograms or the units, based off of someone's age and these other different X variables that we're thinking about. So just as a reminder, once again, if we go to File, Options, Add-ins, hit Go on the Manage Add-ins, make sure that Analysis Tool Pack has a check mark next to it. Then when we go to the Data tab, I'll do that excellent. I probably should check that. Hold on. All right, so we go to Add-ins, Manage. We'll make sure that tool pack is in there. Now we go to Data. Why is it not showing up here? Let me try reopening these files. That's not the one I wanted. We'll just do Expenses. And then we'll go. See if that fixed it. It's a big file, so if you're trying to open that powerlifting one, it's pretty big. Yeah, so now we've got it. So sometimes in that data analysis tab, I'm not entirely sure why it sometimes has issues pulling up. I think this was an older file, or I moved the file. So we got that data analysis tool checked. We'll go to data analysis. We want to do a regression. We're going to hit OK. So we're going to try to predict this total weight lifted. So we'll go up here so we can see our variables here. So our Y variable, let's choose this total kilograms lifted. Control Shift or Command Shift on the Mac down arrow. The X variable that we want, let's look at start out kind of whether or not maybe we can just predict this based off someone's gender. This is a very naive regression. We haven't included any other control variables. Maybe we're interested in how kind of gender plays a role in this kind of measure of strength or something. So we'll hit OK. So we have this, we have this male variable, right? So let's zoom in on this. It's just a little bit easier to kind of see what I'm speaking about. I'll make this column wider by double clicking there. So we've got this coefficient on male. Now, the interpretation of our coefficient estimates, remember, really what we did here was we said, use total grams lifted as my Y variable. I'm going to have an intercept, and I'm going to have this coefficient that represents the relationship between whether or not the individual is male and their total kilograms lifted. So a 1 unit change in my X variable here, if I have a binary variable or a dummy variable, it's just going from 0 to 1. So being a male relative to a female increases the predicted total kilograms by whatever estimate we get for B. So the estimate is our coefficient, so 275. So if someone's a male, we would predict their total kilograms lifted is about 275 higher. Our p-value, right, is pretty much 0. So remember, we also always start out with this null hypothesis, which is that slope coefficient is equal to 0. So if we find a p-value, right, that's less than alpha, you can reject. So can I reject at, what levels can I reject at here? Well, with a p-value of 0, it's going to be less than 0.1, 0.05, and 0.01, so I can reject at all 3 levels of significance, okay? So I found a pretty significant effect here, right? If I think about how was Excel finding these test statistics, remember that was simply our coefficient estimate divided by that standard error that Excel was giving us. That's where that comes from, okay? We also had kind of the statistic we've been talking about, which is the R squared. So this regression, right, is explaining 53% of the variation in our Y variable, so 53% of the variation in total kilograms lifted. So there's still a lot out there that we're not accounting for. And we have to remember, this is just evidence of a correlation, right? So because we left out so many other things, right, so many other things in the X, or the right-hand side of these X variables, other controls, that this is going to contain a bias, right? And so what would that bias be? So if we go back kind of to the slides that we were using, we said the estimate that I get, so we'll call this, well, I won't capitalize it, we'll call it B hat, right, for that first variable. It's going to capture, right, the true effect, right? So we call that B1, right? And if we want to kind of line up here, I could call this like B1, right? And male here is my X variable. But it's also going to include, if we have other variables that are important that we omitted, that are correlated with both being male and total weight lifted, it's going to pick up those effects as well. So when you think about, there's some other variable, we'll call it kind of X2 or our second variable. It will have its own relationship with the Y variable. And then the rest of the bias was something like this. So what is kind of the sign of our bias? Like what direction are we going to be off? Well, the variance is always positive. The covariance between our X variable that we included and this other variable that we excluded, we can determine, kind of using some intuition. So if I go back to my first sheet and I look at the variables I have here, oh, actually it was sheet 2. Sheet 1 was just the raw data. I go back up here, maybe I think about body weight, right? Hopefully this kept recording okay and it didn't reset everything there. So fingers crossed, otherwise I might be recording this again. So where do we leave off here? So it's likely that a positive times a positive divided by a positive, it's likely that this bias, right, is going to add a positive amount to our prediction that we see, or this coefficient. So B hat 1 is this value we see here. So it's likely that this estimate of 275 is too high, right? And we can test that because in our original data, we do have that body weight variable. So one thing that I think talked about in previous classes, I can't run this regression if the two variables I want to include aren't right next to each other, the two variables on the right-hand side. So I'm going to insert a column just so that I can move this male variable right next to body weight. And I'm going to delete that extra column that I had. Okay. So I'm going to go then back to the data and then data analysis, regression. I still want to look at my Y variable being total kilograms lifted, but now I want two X variables, so body weight and male. Control Shift or Command Shift on a Mac down arrow. Got our labels selected, put it on a new worksheet, hit OK. So we can think about that first regression we ran. Let's just call that kind of our naive regression, right? We only included one variable. We had a lot of other stuff we knew probably mattered, but we didn't include it. Here, we added that body weight variable. And what we can see, if we zoom in here, is that once I included that additional variable, my R squared went up. I'm now able to explain more of the variation in that total kilograms lifted, right? 65%. And if I look at my estimate on male, it fell quite a bit, right? Almost 80, right? And so we knew that we probably had this positive bias component, but once we include that variable that we were leaving out that mattered, right, that was correlated with both total weight lifted and male, well, now that bias has been eliminated, right? So we get the effect of kind of an additional kilogram. Remember, the interpretation of the coefficient is one more unit in the X variable, so one more kilogram of body weight would predict the Y variable goes up by 3.15 kilograms, because body weight was in kilograms there as well. The male variable and body weight variable are still significant. The p-value is still approximately 0. And why that is the case is because just like with other sample statistics we were looking at, whether it was like the sample mean or the sample proportion, higher sample sizes, greatly reduce the distribution of that sample statistic that we see. So, stop share here. So what we're thinking about here is that we're actually looking at, we got one estimate for B hat or beta hat, right? It'll be normally distributed around whatever that true coefficient is. Now, the problem is we can't observe that. So we've assumed, right, our null hypothesis was always that slope is equal to 0. Now, as we take a higher and higher sample size, basically the standard deviation, or the, I think about the standard error here, the variance, greatly reduces here. So if we get a smaller variance, what that means is if 0 is in fact the true value, we should make it so that if 0 was in fact the true the true value of B, what we could see for the estimates of that would be really, really close to 0, right? So if I see anything that's kind of further from 0, well, that's going to make that seeing something that far from 0 even less likely when I have a low variance. So what we're going to do is, when we have that high sample size, it makes it a lot easier if we find something other than 0 as our estimate, a lot more likely we can reject the null. So if we look here, right, we've got p-values of 0, so we can reject that null hypothesis. We can reject that the relationship between body weight and total weight lifted and male and total weight lifted is something other than 0, right? We can reject 0 as the true population value, okay? So it's just another good example where we could see this idea of the omitted variable bias and how that impacts these estimates, and kind of reminding us that if we're running naive regressions, right, it's likely that this is picking up a lot of additional effects from other things, right, not just being male. And so once we can control for some of those things, that'll alter those estimates. So we need to be careful. There's evidence of correlation, right? But if we can include more control variables, right, we can eliminate more of that bias, because I kind of showed here just the bias that would exist if there was one other variable out there that mattered. But let's say that there's a third. So we would have an additional, get this typed out here, we would have an additional bias component. So when we included that second variable body weight, we eliminated this bias component, but now this one still exists. And there could be a fourth variable and a fifth variable, right? So let's see what happens. Right? If I go back to my sheet 2 data analysis, click on regression, keep using that same Y variable, but now my X variables, I'm going to include body weight, whether or not they're a male, their age, and then these 2 variables which kind of represent what types of equipment they could use in the meet. So those might matter. So we select all those, hit OK. Now we've got all the controls that are in our data set. Right? So let's start to look at this. So we'll go zoom, 200%. Once again, all the p-values are 0 because we have this 86,000 huge sample size. Looks like male still has a similar effect to what it did before, right? But it did alter. It did drop that estimate a little bit, 196 to 189. It looks like, being another year older, right, one more unit of this X variable, so 1 year older would predict that someone lifts 1.5 fewer kilograms. And then if you were in one of these divisions, you would predict that the amount lifted was this much lower, 134 or 98 kilograms, depending on which division they were in. So what we could do is go through and determine which of these we could reject the null. So let's assume, I'm going to alter this just to give us a kind of more some interesting values. So let's assume my p-values were something like this. Just throw in a couple here. One thing I could do right next to this is use something that we have before, which is use this if statement. Now I can only test against one alpha here. I mean, I could do several columns and to do different ones, but let's just see if we can determine which of these relationships or these coefficients we could reject the null, right, at the 10% significance level. So what we're going to do is say, look, if this p-value is less than 0.1, right, comma, put in the word reject. If it's not, put in the word, oops, failed, let's fall, not fail. There we go, fail to reject. So what that's going to do is for each one of our coefficients, each one of our variables, tell us whether or not we can reject the null. So we'll hit OK, copy this down. Now we can see we would only be rejecting if the p-value is less than alpha. We used an alpha of 0.1. And the only one that's not less than 0.1 is on age. So sure enough, it put that we failed to reject there. Okay? Or we can kind of say, were these variables kind of significant at the 10% level? And if we can reject, we say they are significant. If we fail to reject, we say they're not significant. So if we really wanted to, we could change this instead of being rejecting and failing to rejecting to be saying something like significant. No. Significant. Copy this back down. There we go. Okay. I could even take it a step further. Maybe I actually want to put the alpha value I'm interested in a cell. Now, instead of putting in the number, I'm going to make the cell reference. Okay. I want that to stay the same, so I'm going to freeze that cell. Now, when I copy this down, I can then kind of start to look at different alpha values, and then some of these are significant at the 10% level, but not the 1%. Okay. So we'll change this back to 10% then. Okay. I could also do, when I have these results, one thing that we can think about is what I really have here is a regression where I've got total kilograms lifted as a function of all these different variables. So really, oops, I forgot. Here we go. Plus all those other variables, right? So once I have the estimates for the intercept A, the coefficient on body weight, male, etc., I can plug all these coefficient values in, and now let's say I've got someone who I'm trying to make a prediction for. Right? I'm going to zoom out a little bit just so we can see everything on the same thing. I didn't think it would be quite that big, so apologize for that. So there we go. So let's say we've got someone who is, I don't know, 80 kilograms. Right? They're male. They're, I don't know, 33. They lifted in the raw division, which means they didn't lift in this wrap division, right? So now for this individual, if I had all the coefficients plugged into this equation, I could now plug in that individual's variables for the X1, X2, or body weight, male, age, etc. And then just basically a really simple math equation here to predict what the total kilograms lifted this individual would lift, right? So next to here, I could say, okay, just take that coefficient, right, B1, multiply it by that person's body weight, which is right here. I copy this down. Now, for example, age, it's going to take the coefficient on age, B3, multiply by the age of the individual, and then to get the total prediction, right, that function or that equation right here is telling me to add these all up. All right. Now, that would give me the predicted total kilograms for this individual. Now, one issue I have here, I forgot something, this intercept. The intercept is always going to be added into that prediction. So a real easy way to do that, I could just simply say, okay, put a 1 in here. Now when I multiply the coefficient by 1, oops, if I do this, there we go. It's just going to put that intercept in there, and now I make sure that my total equation adds up from the intercept all the way down to this last one. Right? So that's how we can make some pretty quick predictions in Excel with this coefficient, these different coefficients. And then, it's really just like, okay, let's say the person is, I don't know, 90 kilograms, they aren't male, they're 24, they didn't lift in the raw division, but lifted in the wrap division. We get their prediction as well. And we have it all set up to do that pretty quickly. Okay. So this is just kind of the first example that we're going to go through. This really has anything that you can think of that I could ask. We went through a lot of stuff here that I'd be asking you questions on the exam, that fit the Excel assignment. And I will post this kind of completed version of it on Canvas after I'm done recording today. So you can kind of have that as a little bit of a template. Okay. So I'm actually going to save this so that I can post it later. All right. The next example I want to work through is this expenses file, right? So there's one thing that's a little bit tricky. So let me make sure actually that I open that file up. We've got data on, let me zoom in here so it's a little bit easier to read some of these titles. So basically this was information on different schools, right, different universities, their total number of undergraduates, right? And the other variable that I'm going to kind of be interested here now is their team's basketball expenses, right? So last class we worked through an example where we said, potentially, success in NCAA basketball could increase the total number of applicants, which would subsequently increase total number of undergraduates. But even if we didn't have that story behind the scenes, let's just say I want to run this regression where I'm looking at how is my team's basketball expenses, how much is being spent in the program, how is that impacted maybe by the total number of undergraduates? So there might be some, you think maybe there's a couple issues with regression, but let's just take it as it is. We think that somehow if you have more undergraduates, there's more money at the university, you can spend more money on your basketball program. So that's kind of our idea. So I could go to data analysis, hit OK. So my Y variable here, the thing that I want to predict is what the team's expenses are. Okay. The X variable I think is maybe driving part of that is the total number of undergraduates at those universities. I selected the labels. I'll put this on a new worksheet. So we'll go over here. And we'll say this is, I'll just call it red one. Okay. So let's zoom in here. So we're explaining about 20% of the variation in basketball expenses by just including this total undergraduates. So if we think about the regression equation we have, it looks something like that. So the interpretation here is that for an additional student, additional undergraduate, the expected basketball expenses go up by $125, right? So that's kind of our 1 unit change in the X variable causes the predicted Y variable to go up or down by whatever this coefficient estimate is. It's very significant. Remember, e to the negative 149 would mean move that decimal point 149 spots to the left. So this is pretty much a p-value of 0. Okay. And we didn't really have a massive sample size here. So this is kind of probably evidence of this relationship. We definitely can reject the null that there's is definitely a relationship between these two variables because that null was that it was equal to 0. So we're rejecting that the relationship is equal to 0. We found pretty strong evidence that it's not. So that might be an easy one. But sometimes when we have data, it might be presented in different units. So here I kept the units pretty easy. Just, 1 unit was 1 student, 1 unit here was $1. But what if the data had instead, been given to you in thousands, right? So this is like $637,000, right? Well, now each unit change that I see in this variable, right, is actually representing a $1,000 change. So if I go to my data analysis, now let's say the only data I had was columns M and N. So I'm still going to use expenses as my Y variable. It's just now its units is in the thousands. And my X variable, I'm still going to use undergraduates, but I'm going to use this undergraduates that's in the thousands, right? Because we're assuming that's the only data that we could observe, right? I selected the labels. I'm going to put it on a new worksheet. I'm going to move it over. I'm going to rename it Reg2. And I'm going to zoom in for us. So notice that R squared is the exact same. It shouldn't have changed because the only thing we changed was the units that this X and Y variable were in. So now if we're kind of making this prediction, right, we've got total number of undergraduates in the thousands, right? So if we think about what a 1 unit change would be here. It'd be 1,000 more students, right, would predict, right, because 1 unit change now is 1,000 more students, would increase the predicted y variable by 125. But it's not 125 students, it's 125,000 students, right? Which seems crazy, right? But increasing her undergraduates by 1,000 is relatively difficult to kind of do for any one individual school year to year. Okay? So, and the reason why it's 125,000 students is because our y variable from that second regression was also in the thousands. Now, if we think about this coefficient is exactly the same here, well, it should be, it's just the interpretation was a little different, because think about if I want the, if I go back to my first regression where it was, everything was just in, $1 and 1 student. Now, if I think about, if I wanted the effect of 1,000 more students, right? Well, if the effect of 1 more student is $125 increase in expenses, the effect of 1,000 would be, well, here's the effect of $1, or sorry, 1 more student times 1,000 more students. It would predict that 1,000 more students would increase expenses by $125,000, which is exactly what our interpretation was here. So, I don't know, it's just kind of interesting to see that you're going to get the same effect no matter what the units that your x variable is in. It's just here, maybe it took us a little bit more time to find the effect of a $1,000 change. If we then go back here, let's say instead that the data that we had was, let's say our y variable, we still want to be expenses, right? But we actually, let's say now assume that we have these first 3 columns. So let's say I use basketball team expenses where the units is dollars. So I'll select that row. The x variable I'm going to use is undergraduates, but the units for undergraduates here is going to be that this was representing the 1,000. So 4.9 was, 4,900. So I hit OK. I can look at this output. I'm going to notice now my estimate, oops, zoom 200. Now my estimate looks a little different. Now we've just changed the units, so R squared is still the same, right? But now if I think about what's the interpretation here? Well, now if I've got undergraduates in the thousands, right, a 1 unit change would be 1,000 more undergraduates would change the predicted basketball expenses by whatever this amount is, which is 125,000. Notice we were looking at the effect of 1,004, it was that same value. So it's not that the kind of, oops, sorry, let's move this over here. Oh, I grabbed the wrong sheet. Sheet 2 back here. We'll call this Reg 3. It's not that really the correlations that we're finding are changing, it's just the interpretation that we make is going to be a little bit different, because it's always a 1 unit change in the x variable causes the predicted y variable to go up or down by this amount. And if the y variable is in a different units, this might look a little bit different, but the ultimate interpretation is still going to be the same. Sorry, interpretation. The ultimate correlation is still going to be the same. Okay? So this is an example where we can see the units of our x and y variable not kind of looking like these traditional 1 more inch or 1 more dollar, but instead a unit that represents $1,000 increase, or I don't know, 100 pound increase or something like that. Okay? So I know there's a couple problems on the 5th Connect homework that kind of have some examples like that, so I want to make sure we work through one, but really the same general principles apply. Okay. All right. One more thing I did want to mention, now that I forgot to do on this power up to 1, I did want to mention, notice when we added body weight, we had that R squared of 65 or 0.65. Adding in additional control variables here, increase that R squared up to 0.71. So, that is, as we add in more control variables, typically, we would see we're able to make better predictions or explain more of the variation in that Y variable. Now, we could look at this same thing with expenses, right? I just hadn't included any additional controls. So let's say we want to do, I don't know, isn't going to make probably a ton of sense, but we can do it. So let's say I want to use team expenses as my Y variable, X variable. We're going to do total number of undergraduates, and then this variable is number of students on in the basketball program. So we'll hit OK. Get this fourth regression. Call this reg 4. Now notice, well, maybe, if I keep hitting 100, my R squared is what, 0.20697. Before it was 0.20696. So what that tells us is when we added in this additional variable, it didn't really allow us to make that much. It didn't really explain hardly anything about the variation in basketball team expenses. And in fact, that would make sense because when we look at the p-value of 0.87, well, we can't actually reject the null here. We can't say that the relationship between basketball team participation, the number of people on the team, and the expenses is, if there's any relationship between those two, right? And so, you know, if we fail to reject that null, really this additional variable isn't helping us explain hardly any more of the variation that we see in that Y variable, right? It went up by 0.001%, right? So just two more examples of some things we've been talking about in linear regression. You know, I'm going to try to keep hammering it next week when we do review, but really the things we want to focus on are the R squared, right? Being able to determine if we reject or fail to reject the null hypothesis, which is that the relationship between the variable and the Y, X variable and the Y variable is equal to 0. Interpreting the coefficients. And I also kind of, when we talked about these test statistics, we simply take that coefficient value divided by that standard error, and that's how Excel is coming up with these. Also, we talked about some limited variable bias stuff. I'm not ever going to expect you, if we go back, I'm never going to expect you to like tell me the sign of the bias, just that there is going to be a difference in the coefficient estimate when we include additional variables. Okay? So that should be kind of all the new material or examples for this semester. We'll be doing review for every single, I'll do 3 kind of review videos next week, same time as class usually is. If you have any questions, I'll use this as a time to kind of do some review, but also maybe like kind of office hours where you can kind of come in and ask for help on different questions or different problems that you're having. Other than that, that 4th Connect and Excel are due today, and then the 5th Connect and 5th Excel are due next Friday. If you have any questions on those, reach out early in the day today, because I likely won't be available later at night to kind of respond to those. Any other questions you might have, please feel free to send me an email, and we'll talk a little bit more about exactly what the exam is going to look like next week. It will be available finals week, which would be what, December, I think it starts the 15th. Yeah, December 15th through the 17th, so that Monday, Wednesday, and Friday of finals week. Okay? All right. I will talk to you guys on Monday.